You can.
I did. Okay. You will. Actually, the video thing is not like part of the lecture. You have to read a little bit more. Okay, let's start. This is at 11. And thank you for coming. Okay. So, more will come. Today, we are going to do ODE. More in ODE. I will review a little bit on what we did. Okay. And maybe ask some questions to review a little bit on integration and interpolation too. So in ODE, we will talk about more accurate method, okay, and adaptive step size. All right. First, let's review about interpolation. That's just two of you, okay. Nan, what did you learn about interpolation? What kind of method? What is the name of the method?
The spline and cubic.
Cubic spline.
Yes, the cubic.
What about the linear interpolation? Did you learn about that?
Yeah, linear.
Okay. Daniel?
Yeah.
By now, can you do cubic spline?
Oh, I could. Okay.
Okay. Open book, open note, everything. You can do cubic spline. You understand that it's a piecewise continuous function, connected dot, get the slope. You know that, right?
Yeah.
What about 2D data? Can you do interpolation for 2D data?
Oh, I haven't studied it, but I think I
You know the concept.
Yeah.
That's actually not enough. You have to be able to do it. Okay, integration. Okay, Daniel, what kind of numerical method that we have learned for integration?
We've learned the Simpson's method
Simpson method.
and the
Trapezoidal. Which one is more accurate?
The Simpson.
Simpson is more accurate. So, Daniel, can you do double integration
Yeah.
with Simpson method?
Yeah, sure.
Okay, so we have to do Simpson method twice.
Mm-hmm.
Something like that. And if you forget, you know where to look at, right?
Yeah.
That's important. After this class, I think you will remember most of the things on the exam day or when you do the project. But like 1 year after this class, if you want to know how to do it, you know where to look at. Okay, that's good. All right. What about ODE? Okay, who's next? 11:02. Not that late. I mean, okay, you're not late. For ODE, what kind of method for solving ordinary equation? ODE, ordinary differential equation. I mean, what method did you learn to solve ODE?
Learn Simpson's 1/3.
Simpson is integration.
Oh.
Trapezoidal is integration. If you have dy by dx equal to some function of x and y, how do you solve it? Of course, you can integrate it, but with ODE method, what are the methods that you have learned?
Let me see my notes.
Let you see your note. ODE, we have explicit Euler, implicit Euler, Ring-and-Coulter method. Have you recall any of this?
Yeah.
What is explicit Euler?
Have to look.
We use the slope at the current point to calculate the next dot, right? That is implicit Euler, explicit Euler. George, you're not late yet. Do you have to leave the class in the middle of the class again today? Every time you do that, like when it's about 12, you will walk out and after a while you come back.
Wait, what? I didn't do that in class.
Really? You stay the whole time, right?
Well, what are you talking about?
Sometimes at 12, you walk out for a while and then you come back in.
It's not in your class, it's on this class.
Okay, implicit Euler. Are you ready, Ami?
Yes.
We solve ODE by using the slope at what point to guess the what
current
point.
The current point.
The current point is explicit Euler.
Oh, the next point is implicit one.
Implicit Euler. So we use the slope at the next point to find the next point itself. So it will be one equation, one unknown, right? So how do we solve one equation, one unknown? I mean,
Any method would work.
what is the name? Give me one method.
We can use Gaussian and then.
Wrong.
No, sorry.
Any method for solving one equation, one unknown, which is Newton-Raphson. Gaussian elimination won't do the job. It is for linear system of linear equation, but you may have non-linear equation.
Oh yeah.
Runge-Kutta method. We conceptually, is it explicit or implicit? I mean, Runge-Kutta method. Did I talk about that last time?
No, yeah, you did.
You talked about
It's
it, right?
explicit.
Is explicit
As far
for Runge-Kutta fourth order?
as far as I remember, yes.
Explicit? Are you sure?
I need a quick review.
Just say yes
Yeah.
or no.
Yes. Yeah.
Daniel, do you agree with him?
Yeah, I think it's just implicit.
Oh, really? Nan, is it explicit or implicit for Runge-Kutta method?
It should be implicit.
Implicit. George, Runge-Kutta fourth order, is it explicit or implicit?
I'll go with the majority.
Implicit. Wrong. It's not implicit, it's
Oh,
Check out with you.
so I mean you were right.
explicit. I mean, you're correct. So, Runge-Kutta method. Who still remember anything? I think I should show you the formula. Because it doesn't seem like you remember anything yet. Formula for Runge-Kutta method. It looked like this. dy by dx equal to some function. So that function can be anything. Can it be sine, cosine? If it is sine, cosine, can you use explicit Euler to solve it? As long as your right hand side can be evaluated, given that you know x value and y value, then you can use explicit Euler, right? For example, if right hand side is sine x multiplied by cosine y, and if you know that, hey, x equal to 0, y equal to 0, you can do the evaluation, right? If you say x equal to 0.5, y equal to 0.5, you can calculate right hand side. As long as you can calculate right hand side, given that you know the formula, it's fine. So one of the requirements is f, x, and y. It doesn't need to be known, but when you input x and you input y, you should get output as a number. So
Not a function.
just scalar number. So dy by dx equal to e to the power of x, e to the power of y, sine x. So if I use explicit Euler, one thing that I need first is initial condition. Okay. Initial condition is at x equal to some value, what is y? Okay, let's say we know that if x equal to 10, y equal to 10. So that is initial value. We need that. So when you solve ODE, you need one condition, right? Otherwise, your answer will be like analytical form, have constant 1, constant 2. But we cannot do that numerically. So we need to know the start point. Alright? And then we need to know we want to solve y value for what range of x. So if I want to know y for the case where x equal to 10 to 20, this means I have to move forward, right? Delta x has to be positive. But if I want to know from the range of from 10 to 0, this means I have to step backward, right? So this means if I use delta x or h equal to minus 0.1, I put x equal to 10 and y equal to 10 in this formula, right? And then I evaluate the right hand side. Then I get the slope at the current point. I use the formula next point, which is y equal to y0 plus slope multiplied by the step. You recall that? This formula. So that explicit method. And if you want your explicit method to be stable, so let's say sometime you did that, it jumped around, you want it to be stable, what do you do, Amir?
Don't remember.
Not remember, there's nothing to remember. Daniel, we do explicit method, it is not stable. But in that case, we use h equal to minus 2.5, right? And it's jumping around, and we try to solve for the case of, I think, e to the power of minus x or something.
We reduce h?
We reduce h. So from minus 2.5, what do you suggest, Amir?
With minus 1 first.
Okay, so reduce the magnitude, right?
Yeah.
Not just reduce. If you reduce h, instead of minus 2.5, maybe minus 10, is that better? Minus 10 is less than minus 2.5. That's not what you try to say. You just reduce the magnitude, absolute value. So, yeah, if you have h to be like 0.1, 0.01, it will be more stable. Okay? It will be stable and your result will be good, accurate. It won't be as accurate as the Runge-Kutta method. So if your Runge-Kutta method happen to be unstable, you reduce step size, you reduce edge, right? Okay, now we finish the review. Question on the review part. No question.
So for the Runge-Kutta, you said we need initial guesses for x and y.
Initial condition. It's not initial guess.
Okay, initial condition.
Initial condition.
Like the correct value of x.
Correct value of y at a given point of x.
So we now base our future estimation on the initial.
So the next point based on that.
Okay.
I have question. If you guys don't have question, I have question. So if instead of this equation, it seems to be easy. I think you can do something a little bit better. What if, let's use bigger line. What if it is something like this? And some function maybe sin x, x to the power of, or e to the power of minus 2x squared dx. So the right hand side is only a function of y. It's not even a function of x, right? So instead of writing sin x, if you say sin z, e to the power of 2z squared dz, it's fine. But the right hand side is only a function of y, right?
The right hand side is a function of z.
No. Is it a function of z?
But the thing you have the limit from 0 to y.
Oh, yes, sir.
We have the limit from 0 to y. So inside, what is a z? Z can be anything. You can change Z to A, to B, to C, to D, to E, to F.
Yeah.
It's just formula. Right? So right hand side is a one function, one unknown. Okay. Can you solve it with explicit order, George? Yes or no?
I want to say no.
I can, and you should. The question is how? George, how do we solve it?
I don't know.
You don't know? Nanjinli. How? This is still explicit order. We are still reviewing, but it's coupled with the material that we have early on, which is integration. We just mix them together. You can do integration, right? You can do explicit order, but somehow when we mix them together, you cannot. Come on. Theoretically, it can be done. How do we do that now?
So first we try to estimate the right hand side by using Simpson method. Then I don't know.
The key is, for explicit order, we use the slope at the current point to get the next point, right? And the formula is, this. Next y equal to current y plus delta x or h multiplied by slope. Concentrate on this equation, okay? So how do we get slope? Slope is right hand side. Whatever it is right hand side, right? So let's go back to our pen. We use a slope at the current point. I have to ask myself, what is the current point? Current point is x equal to 10, but y also equal to 10, okay? Y also equal to 10. What do? I put the limit of integration to be 10. And now, can I use trapezoidal method? Yeah. Can I use Simpson? I can. Right. Not do it analytically. You cannot really integrate, like, or maybe you can, but sometimes you cannot. If function become a little bit more crazy, you cannot do it. So now you just put 10 over there. You evaluate the right hand side. So this means you use the current point to get the slope at the current point, and you do linear extrapolation from that point, right? Good? Okay. Question? I have a question. If you don't have a question. Okay, George, give you another chance. How do we solve it? By implicit Euler. You know how to do by explicit Euler, right? How do we do by implicit Euler? Oh, let me recall you. This session is to review. Implicit Euler is you use the next point, the slope at the next point, to calculate the next y value. So next point is, so this slope is defined as next x and next y. We know next x is just x plus h. But we don't know next y, it is unknown, right? So next y value is current y plus delta x or h and the slope at the next point. Then we have one equation, one unknown. That unknown is y at n plus 1. And you solve it numerically by using Newton-Raphson or bisection method. Okay, let's come back. How do I do this? With explicit scheme. Explicit Euler.
Explicit.
Oh, implicit, I'm sorry.
Implicit. Well, you just said it right.
Can you repeat what I say?
Yeah.
In this context.
Yeah, well, I guess you just have to integrate the thing using Newton-Raphson.
If I follow what you said, I don't think I get a result. So the step one, we have to define h. let's say h is 0.1. Okay? So I said we have one equation, one unknown, right? And we solve it by Newton-Raphson. Who want to help him? What is that one equation, one unknown? How does it look like? Nanchale? He's your friend in undergrad, right? Do you want to help him?
Yeah, but right now I'm trying to help myself.
So can you show us the PDF, the last PDF?
That one equation, one unknown,
Yeah.
it is this equation. Alright? That is the equation that you have to solve. So, instead of, okay, let me add more space. So you have next yn plus 1. Okay, add a minus sign, okay, equal to, oh, not equal, plus yn plus h and f at xn plus 1 and yn plus 1 equal to 0. That is the equation that you want to solve. Specifically, you have to write minus unknown yn plus 1 plus 10, right? Because current point is 10 plus minus 0.1 multiplied by our function, which is integration from 0 to yn plus 1, right? Of something crazy formula, but it's not a big deal. dz equal to 0. This equation has only one unknown, which is yn plus 1. And it is one equation, one unknown. You can solve it by Newton-Raphson. Can you? Daniel? Bisection method.
Bisection.
Yeah, if it can be solved by Newton-Raphson, it can be solved by bisection method.
Yeah.
So it may be a little bit too complicated if you look at it like this. Let us looking at it as g of unknown y equal to 0. Why do we have to look at it as g? Because you have to find g prime, right? And you will need to have like what? G over g prime. You have x minus g over g prime equal to new x or something like that, right? You remember Newton-Raphson? Yeah. So how do you evaluate gy and g prime y? Okay, let's start with gy first. So our initial guess of y will be what? Something close to 10, maybe 11, maybe 9 or something. But your initial guess will be minus 2000, right? Because we know that at initial point x equal to 10, y equal to 10, right? So let's say our initial guess is 11. How do we find G11? I mean,
G11?
yeah.
Simple current point.
So y equal to 11. What do I do with this equation? What do I do with that? I put 11 in. I do substitution, right?
Yeah.
No problem. How do I evaluate the integration from 0 to 11?
Oh, we use Simpson method.
Yeah, okay. Now it's like function inside function. You know how to do that, right?
Okay.
So you can evaluate g for y equal to 11. Hey, George, how do we get g prime?
Another guess, I
slope of function g. How do I get that?
Similar point, isn't
Can you,
it? I don't know.
how do we get g prime? Nan, do you agree with him? He said he don't know. Should you not know? Or should you know that? They teach you how to do it. How did I do it?
So you just use the
Finite difference.
yeah fine.
I use finite difference. Any clue, George? Finite difference. How do we use finite difference to find g prime? Do we do g at 11.001 minus g at 11 divided by 0.001? Do I do that? That is okay. But there's more accurate version, which is central difference. Central difference means I don't use 11.001. I use 11.001, but I minus g at 10.999, and then I divided by 0.002. The point a little bit higher and the point a little bit lower, and then divided by the gap, right? So that's how I approximate slope. Don't just mind, George. Do you understand this? Come on, you just say yes. How may I help you, sir? How do I make you understand this?
I need to wake up.
You need to wake up. Finite difference is this kind of approximation. Okay. So with finite difference, we can get the slope. With the slope and the point value, we can use Newton method. Right? So with Newton method, we can find the unknown in backward scheme. Good? Conceptually, is look good for you? Yeah? Come to see me after class, job. Unless you say, understand. No! Still come to see me after class. Okay, this is just a review. You see, it may look easy, but it can be a lot more difficult. Okay? We haven't done the review yet. You know how to do it with explicit method, implicit method, right? Let's talk about just explicit method, easy method. But this time, I say, hey, solve for the case of x between 10 and 100. And I know that at x equal to 0, y equal to 10. But I ask for the range of 10 to 100. Now it's a problem, isn't it? Then let me erase it and do it very clear. Any thought on how to do that?
So you should do the same thing, and then you take your prediction and 10 to 100. Because you start from 0. Right?
So you can start from 0. And you do until you reach 10. And you keep moving until you reach 100. And you cut from 10 to 100 as a part of your solution.
Oh.
Good? So you can start from 0 to 100, can you?
Yeah.
Yeah. So you get all the data from 0 to 100, and then you cut just 10 to 100 and submit it. That's the solution. Good? So this means your edge cannot be 0.3. Right? If your edge happens to be 0.3, you start from 0. You will get 9.99. And the next point will be, what, 10.02. You don't hit like 10.0. Okay? But that's not much of a problem, you can use h 0.01, 0.02 or something. Okay, Runge-Kutta method. See the formula, and okay, this time I think it will be okay, George. Runge-Kutta method, is it explicit or implicit method?
Explicit.
Explicit method. Okay. So, who want to explain me conceptually how do we do Runge-Kutta method? Like, if you don't talk about the formula, forget about formula. Verbally, can you explain me about Runge-Kutta method? Daniel?
It's an explicit method, and from what looking at the screen, you use the current value of y to estimate the next point for y.
Let me help you then. Okay. When anyone asks you to explain about this, physical meaning, physical expression of this thing is Runge-Kutta fourth order derived from Taylor series expansion. Okay. Based on that, the next point is evaluated by the slope average. It's not just one value of the slope, it's the average of the slope value. And those slopes, they are the slope at the current point, the slope at the middle point, and the slope at the end point. You average those three slopes together, then you can get accurate slope between point 1 and point 2, and then you can get point 2. Okay?
And what average is that?
But the way that you average it is weighted average. You don't give the same weight for each slope. So for point 1, for the current point, the slope at the current point, the weight is just 1. The weight for middle slope is 4, and the weight for the last slope is 1. So you do 1, 4, 1. However, in the formula, it has K2 and K3. Both of them are for the slope at the middle point. But if you look at the formula, we cannot tell what is the slope at the middle point. We cannot tell because we don't have the middle point. Right? We don't have the middle point. How can we tell the slope at the middle point? We cannot. So we calculate the slope at the current point first. Then we do linear extrapolation to guess the slope at the middle point. In the formula, look at this. K2 is the slope at the middle because it is evaluated at xn plus half h, right? So it's the slope at the middle point. But we don't know the value of the middle point. We don't know the value of y. So y at the middle is linear extrapolation based on the current slope, the slope at the current point. Make sense? Look, 0.5h k1 is a linear extrapolation based on the current slope, right? And that is how we get y value at the middle. Y value at the middle comes from linear extrapolation. Then we can estimate the slope at the middle, right? But we think there is a way to improve it. We can make it better. So we say, hey, K2 is the slope at the middle. And this time we do linear extrapolation to get the y value at the middle point, but this time we use K2. It will be more accurate, right? Yeah. So that is K3. K3 is the slope at the middle point based on the linear extrapolation of K2.
So we can do away with K2.
What?
We can actually eliminate K2.
You need to use K2 later. Here. At the end, you need K2 too. So K1 is the slope at the current point. K2 is the slope at the middle point based on the linear extrapolation of K1. K3 is the slope, it's also the slope at the middle, but it's based on the linear extrapolation of K2. And K3 is slope at the end. but the y value is based on the.
K4
Did I
or
turn it
K2?
on?
It's still recording.
Still recording? Okay. So K4 is based on the linear extrapolation.
Of K3.
That's why you use edge, right? Full interval. And the slope value is K3. Once you get the slope at 1 at the initial point, 2 at the middle, and 3 at the end, then you do weighted average based on what you get from Taylor series expansion, which is 1 over 6, 1, 2 to 1 for K2, K1, K2, K3, K4. Weighted average. So this way, you can get the next point more accurate. Fourth order. Good? So when I'm talking about 141, does it recall you of Simpson? It sounds familiar, right? 141, but if you have 141 several times, you have 1, 42, 42, 42, 42, 41, right? So that's why we have fourth order. When your edge reduced by 10 times, the error reduced by what, 10,000 times. Okay? So it's accurate, but it doesn't mean that it's stable. Accurate doesn't have to do anything with stability. It can be unstable. In case that it's unstable, we reduce the step size. Question? George? You kind of fully understand? Do you understand the concept? Weighted average of the slope.
Yeah,
Okay. See you in the class, okay? So this is a review of Ring-Akuta method. Okay. So we achieve our goal, right? Our goal is to review interpolation, integration, and some ODE, solving ODE. But it is first order. Okay. Let me continue.
Sorry.